Okay, last we left off, if I remember correctly. Okay, so we were talking about acids. We talked about acids.
Oh, yeah, weak acid.
We talked about weak acids, strong acids. And so,
Because I checked. And it was a Sunday. I was like, oh, oh, yeah. Not fully. But it was. And then I did it. I did one question, like in the beginning of the week, I was like, oh, excuse me, can I get back to it? It just says, no, no, that was a lie. And this is, I'm already behind in math. I was gonna ask, but I haven't for the same class, so like, I don't go to class, but it's optional. It's only if you need the help, I don't need the help. It's just- I could turn in things late, right? Well, not for this class, specifically, but for math, you could turn it in late.
oh,
Yeah. So I was like, since there's no penalty for turning things in late.
okay, so we'll change that.
See, that's the thing. I want to change that, but I can't.
Don't worry, I will change that.
Well, not here, not here. This class I'm okay with. This class I'm good with. It's just math.
Okay. There you go.
Math I understand. Math I can get it done within an hour.
Oh,
It's just math.
Oh, no, never mind. There you go.
Except for the mathematical definition of what I was looking for.
I'll give her a minute.
Yeah, Dr. Henry. I don't think I went over this.
I'll give her a minute. I think Justin was later, but chilling.
Okay, so we've talked about strong acids and weak acids, right?
No.
Okay, so what is an example of a strong acid?
Yeah.
If it ends with ic, is citric acid, which has carbon in it, is that a strong acid? Are you sure?
No, carbon. No.
Okay, carbon breaks rules always, right? Good. Okay, so we talked about the hydronium ion. You guys remember the hydronium ion? Okay.
I can just go over the hydronia. I remember I didn't get to fully listen.
Sure. Alexandria,
Oh, slide.
can you hear me?
Yeah,
Just making sure. You've had trouble with Yayo. I guess I should probably fix the
Oh,
camera.
yeah, on Monday. I would cut out.
Sorry, Alejandro. Yes. Sorry, wrong person.
It doesn't show up on the regular. It's got to look like. Will be on there.
So the audio didn't work for you at all?
It worked, but it would cut out sometimes. Maybe do this where I'm at.
Okay. That's good to know. Okay, so.
It's okay.
Before we get started, I have a couple questions for you guys. So, if there was a chem, when there is a chem degree, how many of you guys would pursue it? Let's say if there's a chem degree as of today, how many of you guys would consider pursuing a chemistry degree? How many of you guys would consider pursuing a chemistry degree, your associates? Chemistry.
And that would entail what kind of chemistry? Organic? inorganic?
You just have to take this class and then you take organic chemistry. You just
Oh,
have
that's
to
not that bad.
one more semester or two more semesters.
Not that bad. I wish I- yeah.
Three, it would be this class, 1B, and then it would be OChem.
Yeah.
And that's it.
So I just want to idea. So there are new rules that are being established here. So I have to get a little bit of a survey.
Would that be for like associates or transfer?
Yes, yes. So the idea is to try to get an associate's for transfer. So then you guys technically have options. Some of you guys are looking for bio, you're planning to be an MD. So you're gonna have to take organic chemistry anyway, but it's not required for your bio degree at the associate's level. It is required for your bio degree at a, for your BS. So, what was that? Yes, that's right. And so you would get your degree in chemistry as well as the one in biology, because you're taking all the other courses.
Right.
So it's like a two, and then you have an awesome instructor like me instead of, some behavior or something like that. So, so I just want to get an idea because I have to, I met with my admin today about the programs. We're trying to get the physics programs, or we're trying to get chemistry through, we're trying to get computer science through. So those are the 3 programs that we're trying to get through. I know that somebody here is interested in computer science, right?
I am interested.
Yeah, so, and so I need justification. And so if I can sit there and say, I have 10 students today that would be willing, that are interested in getting that degree, it makes it more viable. And so, and then my admin will be presented to the president and the chancellor. So, like I said, new rules, a lot of new rules are going on, and so I end up having 50 meetings instead of a normal 25. So, okay, so let's start off with the hydronium ion. Oh, that one?
Oh, yes.
Wait a minute, I just realized, yeah, I just gave you the. Slides.
Okay, it's all right. Yeah, okay. So that sounds like.
Okay, so we've already talked about H plus just being a proton donor, right? So since H plus is just a proton donor, H plus is kind of weird. It's kind of like needy. I guess had a needy boyfriend or girlfriend. Or you're the needy girlfriend. Okay, so we have an example, right? So in the case of that needy girlfriend or boyfriend, they always have to be around their man or their significant other, right? So they're always right next to them. Oh, I need you, I need you, I need you. Can't let you go. We gotta be snuggled up all the time, right? Oh, you can't go to the bathroom without me. No, 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 right? So H plus is kind of like that. So what happens is that H plus actually finds water and it attaches to water and it's like, oh yes, baby, I love you, and it becomes the hydronium ion. Now the hydronium ion, it still has that characteristic of just being H plus, right? It has an extra proton that's there. But of course, there's water involved in it as well. So it's going to be very similar. So for simplicity purposes, what we do, we just basically use that H plus instead of writing out the hydronium ion, right? But reality, what it is the hydronium ion, okay? Now, the thing is that when acids are formed, if they're strong acids, we get total dissociation, right? We talked about total dissociation. You guys already know how to do total ionic reactions, right? So strong acids are going to totally dissociate. So in the case of strong acid, so we know that this acid is called hydrochloric acid. And so it's going to dissociate into the hydronium ion. if we're just writing for simplicity purposes, H plus. So this is really the hydrogen ion. But we know that it's really the hydrogen ion.
It's off the.
Fun. Work right. Problem is that I use so many words during the week that I forget which one does what.
Yeah.
Yes. Okay. And then we have, what ion is this called?
All right.
Chloride. Guys, remember your nomenclature, right? Okay, so a strong acid is going to completely dissociate. Where we know a weak acid this is acetic acid. Okay, so a weak acid has the ability of doing both, right? But it's only going to partially dissociate. Only a little bit of it's going to dissociate. Now, one way to determine whether or not we have a weak acid or a strong acid is by using electric conductivity, right? So if it's able to conduct electricity, that means that the ions are present. Sorry, it gets wiped out. We're going to eventually get something that will cover this up. Yes. Like some of those simple things, listen to talk to me first before they just put shit in anywhere, right? Nice. I actually think that I consider that. Okay, so ranting a little bit, a little upset about things. Okay, so anyway, weak acids, they're going to exist. Majority of them are going to be still together. So that hydrogen is going to stick to it, right? And if for some reason it's really attached to it, it's not going to want to let go in the situation. Like, unlike here, where it's like chloride is like, do what you want to do. Get away from me, you know? Just get away, right? Go do what you want to do, right? Where here, they're going to be a lot more attached. Spend more time together than apart. Okay? Does that make sense? Okay. Okay, so that's how we determine between a weak acid and a strong acid. Okay? So we can also use the fact that we're forming this H plus ion when we get separation. The number of H pluses, the concentration. We talked about concentration before, right? Molarity, stuff like that. The concentration can actually be used to determine our pH, right? That's really what our pH is. So what is pH? What do you guys know about pH?
It's exponential.
It's exponential, okay. What else do we know? So you said it determines whether something is a base or an acid. So how do we know that it's a base or an acid based upon its pH?
Base is 7, right?
If it's
7 is
seven,
neutral.
7 is neutral, so
Oh,
pH
there
is
you go.
7
Oh,
is
and
neutral.
anything higher than 7 is a base, right?
So if it's higher than 7,
And below 7 is an acid.
okay. So we also know you said it was exponential. So for determining the pH, pH is going to equal minus the log base 10, the concentration of our H plus ion or our hydronium ion. Okay, so if you're given a pH, let's say we have a pH of 3. So then, if we want to determine its concentration, we would just take the inverse of the log. What is the inverse of log base 10? That would be the inverse of p. Okay, we use L, right? So what would be the inverse of log base 10? You're supposed to know this, right? Nope. What is the inverse of log base 10? Okay, so inverse of log base 10 would be 10 to the whatever power, right? So in other words, you would take minus pH, and then that would give us our concentration. So the inverse of the inverse of log is 10 to the whatever power. Right? Okay, so if it's pH 3, then we would have 10 to the minus 3 is going to equal to our concentration. And that would be molarity. You guys remember molarity? I barely did on this. Okay, so if we're talking about an acid and a base, right? Or we have a base. You told me that bases are going to be greater than 10, right? I mean greater than 7. So let's say we have a base. Can I erase this part here? And it has a pH. So our base has a pH of 10.7. Okay. Now, for us to get the concentration of our base, we need to know one other thing. pH plus pOH is going to equal 14. This is based upon ionization of water. And equilibrium constant, which we're not talking about today. I'm just giving you guys a preview, but you kind of need to know bases, acids. So, So what do I mean by the ionization of water? What water naturally does it forms two ions, hydroxide ion and the hydronium ion, or the H plus ion. Okay. And so it's mostly in this form, but there's going to be a little bit that's in this form. Okay. So it's an example of, in a way, of a weak acid. Right? And water is kind of funny because it can act as a weak acid or a weak base. But the thing is that the number of H pluses and the OH minuses are equal. Right? They're both 7. So they're both pH of 7 and POH. Okay. So overall, if we have P of water, it's going to equal 14. So that's how we get this value, right? So anytime that we're talking about pHs, we can figure out how much OHs are in solution by knowing the number of pHs. So if we have a pH of 10.7, what would be the peak OH? Using this equation.
Wait, can you repeat the question?
If we had a pH of 10.7, what would be our peak OH?
17%.
Sure.
Are we saying that pH is 7, right?
So you put in 7 here,
Yeah.
plus POH equals 14.
Yeah.
Sorry, not 7. Put in
10.7. Yeah.
So POH,
Oh, I misunderstood.
POH is equal to set 3.8 or 3.3. I can do more. 3.2. So then this will allow us to calculate the concentration of hydroxide in our solution. Okay, so it works the same way. So if we want the concentration of the hydroxide, you guys mind if I erase this part here so I can have to write it up? So our POH is equal to 3.3. So then if we want to calculate our concentration of OH, that's going to equal 10 to the minus 3.3. Okay, plug that into your calculator, what you guys get? Can you guys remind me, what are the units for molarity? Again,
Moles over liters.
moles over liters.
2 seconds.
Yeah. It's just
5.0 times
5.0 times 10 to the negative. Okay, do you guys see how to do that?
No.
No?
I fell a little behind and I got completely lost.
Okay, let me see if I can clean up my board a little bit. To give us room to actually work a little well. So, let's say we have hey, let's say we have ammonia. Ammonia is a weak base, right? So when we have ammonia, this is what happens. Okay. So when we put ammonia in water, we end up getting the ammonium ion, and we get hydroxide. Okay, you guys see that? Does it make sense? Does it balance? Don't look crazy, right? Okay, so that means that we would expect ammonia to basically be a base, right? Water is acting like the acid, it's donating the proton, it's donating the H plus, right? So then the ammonia is accepting the H plus over here. This here is called the conjugate acid. This would be the conjugate base. Here, this is acting as our base. This is acting as our acid. Okay. So, if we have the pH of this solution, say pH is equal to 11. Okay. So, if our pH is equal to 11.4, what is the concentration of our ammonia? Or what is the concentration of our hydroxide? Okay. What was that? 2.6 would be our pOH, right? And how would you calculate that? Okay, so we know that pH plus pOH is going to equal to 4. Okay, and that's based upon what we call our equilibrium constant. Equilibrium constant for water separating, and it's all based upon water separating into its ionic components, the H plus and the OH. It's going to be 10 to the minus 14. Right? But for right now, I don't want you to know that. I want you to remember this equation. Right? Okay. So write that down somewhere. Remember this equation. Okay. So always, when we're working with acids and bases, we're going to be based upon the acid and base scale. Okay? The acid and base scale goes from 0 to 14. Now, can it go below 0? Yes. Can it go above 14? Yes. Right? But ideally, it goes from 0 to 14 because once we get out of that scale, things don't add up to what it's supposed to. Okay? So, if our pOH is 11.4, what do we know about a pH of 11.4? Is that going to be an acid or base?
Base.
It's going to be a base. So that means that we're going to have excess amounts of the OH. Right? And so we want to put it in terms of the OH. Okay? And the way that we put it in terms of OH is by first subtracting our value. Plug in that 11.4 for our pH plus pOH. 14. We get pOH at 2.6. Okay? So we get that 2.6 part. This lets us know the pOH, or it also lets us know the concentration of the OH that's in our solution. Okay, that's how much OH is over here. Okay, so then to get that to actual concentration, we know that the OH equals minus log base 10 onto for base 10, the concentration of OH. Okay, so that brackets OH, that means concentration. So if we take minus POH equals log concentration of OH, and then we take 10 on both sides, that gets rid of our log base 10, so it's 10 minus POH. That's going to equal 10 log base 10 H, which is just going to equal OH okay. We're out of room. Oh my gosh. Okay. So then if I plug in this, my concentration is going to equal 10 to the minus 2.6. Okay. So then you plug that into your calculator, you guys get an answer. You guys get like 5 or something. Plug into your calculator. It sounds good to me. You said it's equal to 5. So that would be the concentration. Okay, that would be the concentration of the hydroxide that's in that solution. Does that make sense? Okay, so if we're given a pH, we can use that pH to determine how many moles per liter we have of certain things. Okay, that's going to be important here later on when I start introducing gases. Okay, so say important later on the side of your notes, because when I get there, I'm going to point to it. Okay, you guys ready? Move forward. Is that a little bit better? A little bit better? Okay. Don't worry about it. It'll all start coming together and be like, I got this. Okay. Before I forget, so annually there is a Day of the Dead event on campus. I think it'll be in 2 weeks or something like that, 2 or 3 weeks. Our my classes always participate, right? And it's usually outside, so we usually do something really extravagant. Last year we had flames that were all these different colors and everything like that. Well, this is the way it works. I need to go talk to the committee chair and everything like that. But usually there's a competition. Last year they didn't do a competition, but ours would have won anyway because all the kids were around ours, right? Because it was a bomb ass altar, right? So I would like you guys to design the altar this year, right? For extra credit points, of course, you know. And if you guys happen, if there is a competition and you guys happen to win, I'll throw in some extra points to it, right? So if we're just competing, getting together an altar, right? I'll give you guys 3 extra credit points. If you guys actually win the altar competition, I will add on another 4. So that's a total of 7 extra credit points. That's almost a full grade, right? On a test. Okay. So I would like you guys to work together as a unit to design the best altar possible. Now, I'll have to tell you this. You guys will be competing with my evening class, right? My 2A class. Now you guys should kick their butts, right? But they're gonna give you a good competition, right? So, and because they just got their test back and they didn't do so well, so they're gonna be striving for those extra credit points. They're gonna want to stab people for it, okay? So you guys better bring your A game, that's what I'm saying. Okay, so you guys, is that cool?
Yeah.
You guys can handle that? So anything that you guys will need, right? Anything that you guys think you may need, right? Let me know. And then I will see if I can provide it. And of course, safety is always an issue. So we're gonna have to play within some parameters and stuff to make sure that that safety part of it is taken in consideration as well too. Okay. Okay. So back to acid and bases before I totally forgot. So many things going on. Oh, also one other thing. Your next exam is going to be coming up and it's actually going to open next Wednesday. Right? It's going to cover chapters 3 and chapters 4. You'll have a whole week to get it done. Right? A whole week to get it done, but it's going to open up not today, but next Wednesday. So the practice exam will open up that day, and then later on that day, your real exam is going to open up. So you have a full week to get it done. Okay. And then so we're gonna hopefully finish chapter 4 by Monday. Right? That's the plan. Finish chapter 4 by Monday. So then you guys will have a full week to kind of digest and work out the problems and all that stuff. It's going to open up on Wednesday.
Oh,
Yes. So your practice exam is going to open up next Wednesday. Your exam is also going to open that next Wednesday, but it's not going to be due till the following Wednesday. Okay. So you'll have a full week to get your exam done. Okay. So just giving you guys a heads up. My computer is just acting really slow today. Okay, so as we were talking about, we talked about a strong acid, right? So again, what is one definition of a strong acid? How do we define a strong acid? It completely dissolves, that's right. But an acid in general, we call it a proton donor, that's right. Okay, so this is just that example. So here, they're actually bubbling in hydrochloric gas. Well, hydrochloride gas, hydrochloride, hydrogen chloride. Hydrogen chloride gas is bubbled in. When it's bubbled in, it's covalently bonded. As it goes through that water, it becomes an instant acid. And then that acid completely dissociates. Okay. So when we think about it, when we use G, it's in a gas state. It is covalently bonded. When it's AQ, it is ionic. Okay, so that's going to be really important for us to remember. So we know that strong acids will completely dissociate. These are some strong acids: hydrobromic acid, hydrochloric acid, hydroiodonic acid, nitric acid, perchloric acid, chloric acid, sulfuric acid. So if you have per typically means it's going to be a strong acid, right? Okay, now there is one exception, one of those X that isn't carbon based, and that's hydrofluoric acid. Hydrofluoric acid is a weak acid. Hydrofluoric acid is a weak acid. I'll share it on the screen over here. It's the one in purple. Hopefully it shows up purple on the screen. Okay, hydrofluoric acid. Now there's all the other stuff. This guy is a weak acid. Now, you're going to ask me why it's weak acid, right? Because, you know, hydrochloric acid is strong acid. They're in the same group. Groups behave the same way, right? So your mind, you should be saying, why is that a weak acid? It doesn't make sense, right? That's what you should be saying, right?
Yeah.
Okay, that's what you're saying. Good, I want you to say that because you need to say that. Okay, so let me explain to you why hydrochloric acid is a weak acid. The reason why hydrochloric acid is a weak acid is because fluoride has such a strong electronegativity. Electronegativity is the desire to gain electrons or to pull electrons towards you, right? So what it does, it gets hydrogen. Have you guys ever met a person that was in an abusive relationship? Like, and then their partner never let them go anywhere or do anything.
Oh, yeah.
They kept them tame, you know? Okay, so fluoride is like a super bully, right? It keeps its partners tame, tight to it. And so it keeps that hydrogen so tight that it doesn't want to release it. It doesn't release that often. You know, it barely gets a chance to go to the bathroom by itself. That's how tight it is, right? So tight, right? Not only being needy, this is like beyond needy, right? So because of that, it's a weak acid. It doesn't want to let go of that hydrogen. Won't let it go, okay? Because of that, it stays together for the majority of the time because of the electronegativity, okay? You guys do me a favor, in your packet, page 6. Page 6 in your packet. Let me see if I can pull it up. Nice. Actually, I pulled it up. So if you guys go to P table, and there is all of these different characteristics or properties of the elements. If you click on those properties, it'll actually show you that particular properties for all the elements. Okay. So if you guys take a look here on P table, stop a little bit. Fluoride has the greatest electronegativity. The highest value for electronegativity is 4. Fluoride is essentially at 4. It's like 3.98 to be exact. But if you guys look on your table, it says 4. It's page. Yeah, that table right there. This page right here. Okay. So let's see if I have my chemical packet. Make our lives a little bit easier too. Open sometime today. This is the old one. Yours is new. I have to find it. It's hidden somewhere here.
So how is electronegativity separate from regular negativity?
Because electronegativity deals primarily when they're sharing electrons or that potential of sharing electrons. So it's not a total positive or negative charge. But since, like I said, hydrofluoric acid is kind of, I mean, it's a little different, even though it's plus or minus, it's still going to have that extra pull associated with it because it's so tiny. So fluoride is one of the smallest elements on the periodic table, not the smallest, but one of the smallest. And that's because it's pulling everything so close together. Because of that, it's also going to have an effect on the atom that's next to it or that it's attached to. Okay, so in that case, it would be that hydrogen. Even though it's an ion, it's going to be pulling it really close to it. It's not going to want to let it go. So it's like Napoleon, like was thought to be a bully, right? The short guy, he's just, I'm taking over the whole France and everything, right? Same concept. Chlorine is kind of like Napoleon. Okay, so you guys look on the table. The highest value is 4. So fluorine has the strongest electronegativity. If you guys look on the other side, francium has a 0.7. That has the weakest electronegativity. Okay, in other words, francium is like, hey, really don't need an electron. You could have it if you want it. I don't care. I don't want electrons. Keep them away from me. You know, that type of situation. Where fluorine is like, I need it. I want it. I gotta have it. Okay, and it's gonna have a really strong pull. So it's primarily dependent when you're sharing a bond, sharing of electrons. So that means that the electron is spending more time around fluorine than it's spending its time around the other element. Okay. Does that make sense? Again, we'll talk more about it once we really get into bonds and Lewis-Dot structures, things to that extent. Okay, questions, concerns? Good. Okay, so if I go lecture. So weak acid, we know a weak acid is going to partially dissociate, right? So, and I gave you guys examples of that earlier. So another example, here's acetic acid again in water. And you guys can see that it's the equilibrium sign, arrows going back both directions. So it's known that only 1% of the acetic acid dissociates or ionized. Okay. So that means like 99% of the rest of it is all stuck together. Okay, so here we have most citric acids. They have, or most citric fruits like grapefruit, lemons, they have citric acid. So we know that citric acid is a carbon-based acid, and so it's going to be a weak acid. Vinegar, which is acetic acid, is also a weak acid. Now bases are going to work exactly the same way. Ones that completely dissociate in water, they're going to be strong bases. So bases like sodium hydroxide, group 1 metals with hydroxides are always going to dissociate. They're going to be anxious to separate. They're going to be soluble, remember, right? Okay, and so the process is exactly the same. You see the OH, you see the blood in water, it's going to separate into its ionic components. Weak bases are only going to partially dissociate. I gave you that example with ammonia. You guys see it up there, right? And so the majority of it is still going to be together, but you're going to have a few of them with the OH, right? Okay. Now ammonia revolutionized agriculture. Right? The fact that we can actually make ammonia, we'll talk about that next semester, how you can make ammonia from the air. And so like before, they would have to rely on poop, you know, all of our fields, they would go and get manure and put it in the soil. Now we actually are able to make the ammonia that's needed for fertilization and stuff like that. So it's all synthesized. It's changed the world. You know, there's no reason that people are starving for food because we can make so much food as a result. We also use it for cleaning, right? And you guys know you're not supposed to put ammonia with bleach, right? So, and that's because it makes mustard gas. You guys know what mustard gas is?
They used it in World War II, that's all I need to know.
Yes, it's also chlorine gas.
Yes.
Yes, so chlorine gas, it's a mustard color. So yeah, there was a time period, a lot of cleaning ladies there was this whole rampant death of cleaning ladies because they would use bleach and ammonia in their cleaning solution. So they actually started a lot of, you have ammonia-free cleaners now and stuff like that because to keep cleaning ladies from killing themselves. Because they would be in bathrooms and stuff that didn't have a lot of ventilation. And then they'd go in there and clean it with bleach and ammonia. And you know, you think about it, oh, I have these two super great cleaners. If I put them together, I'm gonna have the most incredible cleaner, right? Not only that, they had the incredible cleaner that actually killed him too, right? So they would find a lot of cleaning ladies dead in the bathrooms of their cleaners. Little history there. So, important lesson, no ammonia and bleach. Okay. So we know that if we put an acid and a base together, we get a neutralization reaction, right? And I'll give you the most classic one on the board, and then you guys can obviously see this one. But okay, so what are going to be my products?
Sodium chloride and water.
Sodium chloride. Okay, we know that this is also a double replacement reaction or Swingers reaction. These guys are going to hook up. We know from our solubility table, or just the fact that we know that group 1 metals are always going to be soluble. When we put in water, it's always going to dissolve. So we know that that's going to give us an AQ, but we know that water is going to be a liquid, right? Okay. So if we're doing the total ionic equation, what would be my total ionic equation? Did that last week, I don't worry, all that stuff out. So what happens to that hydrochloric acid? Separates to what? A hydrogen ion, right? And chloride ion. Okay. What happens to sodium hydroxide? Thing. Okay. So what are going to be our products?
Sodium.
You know, if it's a solid, liquid, gas, you just drop it down. I'll fix that and take that out about that. Any day now, those blinds will be ordered, right? Guys, if you finish the class, I'll find that happen.
Probably. Come on in.
Just to start talking about it. Okay. Okay. So, and then that's for our acid neutralization. So at the end of the day, who are the spectators? Okay, so then we're just left with okay. Questions? What was that? This is a neutralization reaction. So why do you think it's called a neutralization reaction? Because there's neutral. What is the pH going to be? Since it's just water, pH 7. So
There's no free H, there's no free OH.
that's right. So pH of 7. It's neutralization. Okay. Questions? Yeah. Questions. Okay. So let's move forward. Okay, so this is another example of a neutralization reaction. Here we have magnesium hydroxide, and we're putting it in as a solid. But we know that as soon as we stick it in that solution, it's going to dissolve into its ionic components. So then we end up with magnesium chloride as our salt, and we end up with water. Okay, so neutralization reactions, we typically get an acid plus a base. It's going to equal salt and water. Okay. Okay. So the next thing that we're going to talk about is redox reactions. Okay. So I'm going to introduce you guys to oxidation reduction. Then we're going to do a couple of problems. Okay. So oxidation and reduction, or redox for short, reactions are basically when electrons are being transferred. I told you that chemistry is about either sharing electrons, taking electrons. Well, we know that electrons are going to be transferred from one thing to another. Okay. So we're going to do it on the sideboard, even though it's on the screen, so that it'll make a little more sense when we break it down. Okay, that's okay with you guys? Yes. Okay. And I find that you guys, if you guys are just looking at it on the piece of paper, you don't write anything down, you just say, what's on the paper already? Don't get all the good and juicy stuff. Okay, as we go, I'm gonna write down the rules. I'm trying to write it on the side. And then we'll talk about recap the rules. in our lecture notes. So we had sodium. Chlorine gas. Yeah. And make. Chloride. Okay. You see that? So we know that sodium chloride is that balanced for stuff?
Yeah.
Balanced down, right?
Yes.
Okay, what we're gonna do is we're gonna break it down to two reactions, two half reactions. Okay, one of those half reactions is gonna be sodium. Maybe. We know that this is an ion, right? Just remember that, sodium chloride. Ion. So we're just gonna break it up into what's ionic chloride. Okay. And then the other one, we're gonna break it up to chlorine gas. Chloride. Okay. So if we take a look at this, we have sodium and sodium ion. Now, when we do redox, oxidation is going to be loss of electrons. Okay. Or the way I remember it is, I call it beta. Loss of electrons, oxidation. Reduction is the gain of electrons. Okay. So now if we take a solid, what is the charge on a solid? Sure. Sodium. Sodium. Any element on the periodic table, what is the charge on? Take the element as it is. Talked about this last semester.
That wasn't here last.
I mean, last semester. Last section. Right. Sodium metal. Sodium that is from the periodic table. What will be the charge? Total charge associated. Not when it's an ion. Anyway. Nope. That's when it's an ion. It becomes an ion, it becomes +1. When it's not an ion, when it's just the metal that we're talking about, where it hasn't lost its electron. What is it? What is the charge? All elements have the exact same charge. Again, it's neutral, right? Because remember, the number of electrons equals the number of protons, right? Okay, so we know that it's neutral. So when we're talking about, we're going to call this oxidation numbers. The rule number one rule for oxidation numbers is all elements have an oxidation number of 0. That's our very first rule. Okay, so the way I do oxidation numbers, it's different than some other people, but I write the oxidation number on top. Okay, so we know that Cl2, what is Cl2? Is that an element? It's a compound, are you sure? What is the definition of a compound? We're going back to the very first week of class.
Two or more of the same elements? No, that's two different elements.
Okay, two or more different elements is a compound, so it's not a compound. What is it? It's a molecule, and have no fear of isotope. What was that? It's also a diatomic element, so it is considered an element. So what would be the charge on it? What did we just say? What was that rule? Number one. What would be the oxidation number on it? 0. Yep. So its oxidation number is 0. Now, the second rule for oxidation numbers our second rule is all ions have the charge of that ion. Okay, so if we have a sodium ion, what is the charge on the sodium ion? Come on,
+1.
+1. So then its oxidation number is 1. Okay, so if we look at it and we look at electrons being added and taken away, if I'm going from a 0 to a +1 charge, am I taking away electron or am I adding an electron?
You're adding, wait.
I'm going from 0 to a +1. Am I taking away an electron or am I adding an electron? I'm taking away an electron.
Yeah.
Okay. So the way that I would show that is I would say plus, this is the symbol for electrons, E minus. Since there's only going to be one that's going to be taken away, right? Because we're going from 0 to +1. Then you write it down. Okay. So this here, since an electron is being lost, it would be called what? Loss of electrons. It would be called what?
Leo.
Yes, Leo. But what does Leo stand for? What is it? Loss of electrons mean that we're oxidation. So this guy is being oxidized because it's losing an electron. Okay. So here, okay, so now I'm going from Cl. So what would be the oxidation number for Cl minus? So if I'm going from 0 to -1, am I gaining electrons or am I losing electrons? I'm gaining electrons. So then I would add electrons here. And it's gaining 1 because I'm going from a 0 to a 1, but there's 2 of them. So we're going to have to add 2 electrons to make it balance out. Does that make sense? Okay. So this is called reduction. Okay. So the next thing that we would do is, because there's 2 electrons here and there's 1 electron here, we have to multiply that very first equation by 2. So we end up with. I'll write it down here. 2 Na solid yields 2 Na plus 2 electrons. Okay. So if we add up this equation and this equation, we add those two together, we get the electrons are going to be on both sides of the equations, so they're going to cancel out. We get 2 Na solid plus Cl2 gas, and that's going to yield 2 Na plus 2 Cl minus. So, and then we know that these guys are going to look back up because it's not water. Okay. So we see that the electrons are being transferred from the sodium to the chlorine. Okay. And so, and then we're able to get salt in HCl. So this is an example of a redox reaction, right? So for redox reactions, there always has to be an oxidation as well as a reduction. Somebody has to be oxidized. So who's being oxidized? Sodium is being oxidized, and who's being reduced? Chloride. Okay. So when we're talking about this, we get real fancy. People say stuff. So I'm going to use an oxidizing reagent, right? So in this case, the oxidizing reagent is going to be the chlorine because it causes the sodium to be oxidized. Okay, so I'm going to use an oxidizing reagent, right? And so it's going to be the opposite one. You know, it's going to be the one that's actually being reduced. And so if I said if I want a reducing reagent, who's going to be my reducing reagent? The sodium. Okay, because it reduces the chlorine. Does that make sense?
I guess the one that put the take in real quick.
Yeah. But you write it down.
Yeah.
You write it down.
Yes.
Okay, so those are two other rules about our oxidation. You guys have those rules written down, right?
Yes.
Okay, so let me add some more to it, okay? Okay, so just a reminder, if it's an element, what is going to be its oxidation state or its oxidation factor?
0.
0. If it's an ion, what is going to be its oxidation state or its
Well, it's ion.
the charge? Right?
Charge, yeah.
Okay, so what happens if it's a polyatomic ion? Oh, we'll get to that. That's something good. Okay, there's a couple of them that we need to talk about first. Okay. So if you guys take a look, maybe if I showed you the slides, you guys aren't reminding me of it. Okay. So if we take a look at this, right? So I showed you guys the 2 half reactions. You guys see the 2 half reactions, right? I showed you how you got the electrons. That made sense? Okay. So we said that sodium had lost electrons, chlorine had gained electrons. We gave you the definition of oxidation and reduction. So we know that sodium is oxidized and the chlorine gas is reduced, right? We also said that sodium functioned as a reducing agent or the reductant. Okay. And we know that chlorine functioned as the oxidizing reagent or the oxidate. Right? In other words, it does that action on the other. Right? It causes corrosion. Okay, does that make sense? A little bit, a little bit. Okay, so we talked about oxidation numbers. We'll come back to this. So the very first rule I already told you guys about. The oxidation number for an atom in an element is going to be 0. The oxidation number for a monoatomic ion is going to be equal to its charge. Now we're going to get to the nitty-gritty. Rule number 3. Rule number 3 is actually really about 6 different rules all added together. Actually, 9. Very first one is hydrogen is going to be a +1 when it's with a non-metal. It's going to be a -1 when it's with a metal. Oxygen. Oxygen is almost going to be -2 almost most of the time. So when it's in a compound, most of the time it's going to be a -2, except sometimes it could be a -1 when we're talking about peroxides. So if we have O2, 2 minus, right, it's going to be a -1. And very rarely it's going to be a -0.5 if we're talking about superoxides. So if we talked about a compound that's a superoxide, we know that that oxygen is going to be -0.5. Okay. Now, when it's with fluorine, because fluorine is that bully, remember we talked about? I told you it's going to come up again. So fluorine takes charge. So fluorine wants that negative charge for itself. So oxygen, when it's with fluorine, it's going to end up being positive. So if you just have fluorine there, oxygen is going to end up having to be positive.
Good.
Okay. Now, halogens. Who are the halogens? Group 17. So group 17, those guys are going to be -1, except when they're with fluorine, because fluorine is always going to be -1. Nobody is stronger than fluorine. Fluorine says, I get that -1 charge. I don't care what you say. I get that electron, period. Okay. So all of the other halogens, they're going to be -1, except when they're with fluorine or when they're with another halogen that is above them. So for instance, if you looked on your periodic table, we know that chlorine is above bromine. Is that right? I'm making it up, right? So chlorine, if we have chlorine and bromine together in a compound, chlorine would be -1 and bromine would be positive. It was a neutral compound. Okay. I'll show you on a piece of paper in a second. Okay. Now, the other thing is that oxygen is stronger than all of the other halogens except for fluorine. So oxygen is like the queen, fluorine is like the king. Put in a patriarchal society. I know things are changing, right? I want them to, be even, but it's still talking about that patriarchy. Okay. So we know that again, if it's fluorine, fluorine has dibs. I'm -1. That's it. I don't want to hear anything. If oxygen is there and somebody else other than fluorine, oxygen is always going to be -2. Okay. So here's the last one. The sum of the oxidation numbers for all the atoms have to add up to either 0 if the molecule is 0, right? Or to the charge of your polyatomic ion, if it's a charged polyatomic ion. Okay, so let's give this a test run. We're going to do it on the board here because, you guys see these things and sometimes I think you're seeing them. You're not seeing them. You know what I'm saying? Okay. You guys have all the rules, right? I recommend that you write them down. somewhere? Okay, so let's say we have. Okay, so let's say we have. Okay. So let's OF. OF. Okay. So. First rule. It's an element. Okay, good. It's a compound. Okay. So what would be the charge or what would be the oxidation number for each of the fluorines? Okay, -1. So we're gonna write -1 on top. Okay. So then what would be the oxidation for the oxygen? The oxidation state for the oxygen. +2. Why is it +2? For two reasons. It's with fluorine, and then altogether, there was no charge on it, was there? Okay, so the compound altogether has to add up to 0. So if I have 2 times -1, my fluorine, plus 2, that equals 0. That would be the charge on our compound. You see that? Sure. So I have 2 fluorines, right? Each one I know has a -1 charge. Right? Altogether, there's no charge on our compound. It has a 0 charge. So it has to add up to 0. So oxygen has to be 2+. So that would be its oxidation state. Okay. Let's add up a layer. Complexity. Let's say we add 3. Okay. So what would be the oxidation number for fluorine?
This would be
It'll be -1. What about oxygen? Okay, and we know that because 3 plus -1 times 3 has to equal 0. Okay? Just got that? Okay. So what if I have
hydrogen is a +1?
hydrogen is a +1? Okay. So you have 2 of them. Okay. Sulfur has to be what? That's the case. Two. Right. 2 positive or
Negative.
is okay. Okay. Let's see if we can make it a little more challenging. It's too easy, too easy, right? So what if we have this? What would be the oxidation number for hydrogen? Okay. Will be the oxidation number for oxygen. -2. There's 3 of them, so we have -2. So then, with this equals 0, what has to be the charge on the chlorine? Sure. That equals 0. That's the time. 5 plus 1 minus 6. Okay. See it? Questions? No questions? Yes. Good. We could go for ClO3, and then we have plus, right? So then in that case, H is going to be what? It's 1. Now this would have a single charge, right? So then this would be again -6. I mean -6 altogether. So 2. This one would be in the center, right? Yeah, the whole charge of the whole ion. So if you look at it now, that's 5. 5 times 5 plus times -3. So if we looked at just the ionic parts of it. Okay, so you can break it up into its ionic components if you guys recognize that it's not. Sometimes that's the best way to do it. Okay. Just look up my next one I was doing. You guys want to do one more?
Yeah.
Okay. after we do this, and we'll take a break. How many of you guys finished the metals? River did. Starting. Starting. And you guys are starting? So, I'll let you guys, your group, I guess, go. So then that way, we'll all be on the same page. Now, remember, this is an ionic compound, so you can't split them up.
So yes.
So yes.
Oh, but talking amongst each other, I don't know what you said.
What was that?
I don't know what's going on right now.
You don't know what's going on? Did you write down the rules?
I did. They're all right here, but like.
Okay. So we know that this is an ionic compound, right?
Yes.
So if we know that it's an ionic compound, we can split it up into its
Oh, okay,
ions.
that makes sense.
So what are the two ions that you're going to get from that? Look at your polyatomic ion table. Looking at the board isn't going to help you look at the polyatomic ion table. You got it? Split it up into ions. So you're missing one, aren't you?
I like because this is what's on the
Okay.
board.
I'll give you guys a few more seconds. So what are the two ions that we're getting from here?
Magnesium and carbonate.
Okay, so what will be the charge of the magnesium? Mg plus, right?
Yes.
Because we know that magnesium is group, what metal? Group 2 metal?
Yeah.
Right? Okay, so then carbonate, what has to be the charge of the carbonate? Negative what? -2. Be confident. Doubting yourself, I need confidence, right? Okay, so we know that Mg is +2. So what is going to be its oxidation number? What's that rule? Second rule. What's that second law? So charge on it. 2. So then its charges, its oxidation number is 2. +2. Okay. Oxygen. We know oxygen, carbon has to conform. So oxygen is going to be what? So all together it's -6, right? So you know that each one is going to be 2.
Yeah.
So -2 times 3, right?
Yeah.
And now we know that it has to equal the charge for the entire ion. So it has to equal -2. So what does carbon have to be? So its oxidation state is. So carbon has a 4+ oxidation state. Okay. Piece of cake?
Yes.
Just took a second, right? It's just, it got separated.
Yeah.
You see it?
Oh, I see it, but like how you mentioned at the beginning of the class, that carbon is special or whatever.
Uh,
I wasn't here for that, so I was like, oh, what's wrong with carbon? I know that.
Well, you always, so you pay attention to the rules. So the rules kind of lead you to certain things, and then there's certain things that you're gonna have to do by intuition. So for instance, we take a look at the rules, right? Oxygen is defined. We know what oxygen is gonna be, right? So then carbon has to adapt because carbon isn't part of that rule. Okay, sometimes we get an element that isn't a part of that rule. We have two elements that is a part of that rule. So then you start paying attention to where are they located? Who are they beneath? Right? So for instance, who's beneath oxygen? Sulfur. So if I had sulfur and carbon, carbon is going to confer to sulfur. Now, sulfur has more electronegativity, just a little bit, than carbon, because it's closer to being a noble gas than carbon is. Okay. So let me give you that example. So if I had CS, you would assume that in this case, sulfur is going to act kind of like oxygen. So it's going to have what charges? What oxidation state? -2. So then that means in this case, carbon is going to be plus what? Because it has to add up to 0. Oh, charge. Okay. Okay, so let's go ahead and take a break. Then we'll come back and do a lab.